Yes, so thank you for inviting me. And I will speak about something a little bit different. In France, we have, in geological survey, we have a new program starting, which must replace the old program for mapping. And this new program must bring new concepts, modern concepts for everything. So first it must be 3D. It means that it aims at a description of the underground of the national territory in a more or less continuous manner. This is for?
Just so you can just for people who aren't here.
I'm not speaking
No,
strong enough.
We're recording it, audio recording for
yes.
international.
For international. For FBI, yes.
Yeah, Google, NSA.
Yeah, Google, NSA. Okay, fine.
Put in your pocket. Put in your pocket.
In the pocket.
In the pocket.
Can you make sure it's on? Yes.
So, it must be 3D, so. And it has some requirements. It's to contribute to answer scientific questions. So when you submit a project, you must have heavy scientific questions to answer, which refer to geodynamics and things like that. But must also be usable for social needs. It means environment, water supply, urban geology is very important, risk, mineral resources as well, energy, geothermy, and so on. So it means that projects must have a strong scientific background, but as well they must be concerned with strong technological aspects, which refer to words as database, imagery, modeling, web delivery, interoperability, sharing data, and so on, common platforms for acquisition data, all these terms. So, to start, last year we had what we call the BRGM pilot project in Vosges Massif and DM, and it was driven by University of Strasbourg, Karel Schulman, and his students and his PhD. And we have done a work which was to make a confrontation with the 3D modeling and gravimetric field in Vosges area, which is not very simple area because these are granites, in granites, in granites, igneous, in granites. So, okay, but it was a pilot area to try to raise the problems, how to organize the data, and so on, the first experimental study. So we start at geology, boundary plate reconstruction of the area. The Vosges are somewhere, the little place here, close to Massif of Bohème, and they are separated by the Rheinengraben, tertiary Rheinengraben. So you have Moldanubian, they are in the Moldanubian part, separated by, with the North Saxo-Thuringian area. So the questions, what is the structure of a European crust at depth? What are the mechanisms of crust formation at Paleozoic? And how 3D modeling can help to answer these questions. So here is the first study which was done before, which shows a concept, a geodynamical concept, where the lower crust is first delaminated in the subduction process and then re-exhumated by what Mr. Schulman calls laterally forced overturned, a kind of diapirism which obliges the lower crust to come as a diapier. So This is geological model imaginated from those two geophysical surveys, seismic, gravimetric. So this can be seen on the geological map. This part of the Vosges, central Vosges, is interpreted as a diapirism of the lower granulitic crust associated with magma emplacement. This granite is known as the famous granite de Crète in Vosges. I tell this for this French guy who knows this area. Okay. So the same in the upper crust, you can analyze the deformations due to this diapirism. And RGF provides map, what we call events map. What it's called? Maps at different edges. So this is a map at 340 million years, where you can see the granulate extrusion accompanied by MGK granitoids, and here, and at the same time, deformation of superstructures at source and north of the massif. So there are arguments for remelting of granites, and so on and so on. So this combined geological study and their remelting of all this stuff during an extensional event at 320 million years, something like that. So, first, the intrusion of extrusion of granulates, and a big, during late extension orogeny, remelting of the pre-existing rocks at the upper level with migmatization, xenoliths of older NGK granites, and reworking of older granites. All this area here is composed of this granite. So the geometry and the roots of the granites, anatectic granites, which invades all the previous and which erases all the previous history, is what we will study in the 3D modeling aspect. So, crustal extension is you can extract from the RGF maps the events corresponds to this extensional event. And you have arguments for, so all this reworking of granites have been intensively studied by Karel Schumann and his team. You see evidence, because it's an old story in the Vosges, the fact that people by the past have discovered that on textural point of view, the granites, NGK granites, had orthogonal fabrics. And it's really new that this interpretation is given. There has been a lot of debate about the origin of multiple fabrics in the granites, in the Vosgian granites. A lot of debates and fights. But now this has been studied very in detail. So there are some remeltings areas. And magnetic fabric as well has distinguished two families of magnetic fabric, which allows to distinguish primary fabrics from secondary fabrics, which are used to the extensional overprints of the extension phase. So at the end, the story: delamination during subductions, laterally forced extrusion of lower crust, associated to magma ascent, and then a final detachment phase, which remelts with granitic inversion and general anatexy. So all NGK granites are actually relics of this whole story. So the 3D modeling aspect, which was the aim of the, so here are the people who contributed. So I'll present you what we do with the data and how they contribute to 3D modeling. I will illustrate how we succeeded in building a regional architecture of the model and confrontation with gravity data. So, actually, in this exercise, the geological map is considered as a primary data. No field data real acquisition, which is not my favorite approach, but that's life. So here you get geological map. So this is one of the data. You see very detailed map, homogenized all over the area, which is a part of the RGF program to make homogenized map based on new concept and so on. Drill hole, of course, usual stuff. Orientation data, that has to be separated as magmatic fabrics, measured on the field, magnetic susceptibility, anisotropy, gneissic foliation, schistosity. So we have composite fabrics in the granite, so there is a necessity to distinguish these different generations when you do modeling. And this has to be in the database, the different generation, if you want to correctly use them. So, Rheingraben. So we had 1 year to do the model, so we did not do the model. It was imported from from a Georg project, which is what we call a European frontier project, which aims at countries to build models and to build geology, to describe geology in agreement. So they were built under GoCAD. So we got them as data, primary data, and we imported them in another tool. So this raises the problem of when you have data which comes from different models, how you bring all these models already made in one unique model. Because we had the model is Rheingraben. So on the map, on the geological map, you have Triassic cover, which is also on the Vosges Massif. And you have to make the link between the two surfaces, all the data. So you have to actually you use the model, you sample the model, and you restart to model as if there are punctual data. If not, it's not possible to incorporate models in different systems. So how do we do for modeling? As usual, you have to extract principal So when you see a map like that, here, for example, it is impossible to model this in 3 dimensions. There is a problem of drawing. All these faults drones, we don't know if they do exist really. All these lines here, all this. There is a necessity for simplification. So there is no possibility today to go directly from a map to a model. And it's what upsets all our managers. But that's life. So we have to spend time still to extract principal features from this map. And maybe this principal feature could be after reintroduced in the database. I don't know. But it raises the question of how, with a database, because this is considered as a database, how we go from database to model, and how we manage the multi-scale modeling. So for now, it's just a human brain who draws this line from this map. And you can see that this is not a fault on the map. But here it's a fault. So generalization is not just to group all, to try a way to group all these little lines, because in some places, when you change of scale, something which is not a fault becomes a fault. Something which is a fault disappears. So the rules are not so clear. So necessity to capture the contours at an appropriate scale to model resolution. So you all know that. But it's good to point out it every time. So the models we did, different scales for different applications. So we propose a regional scale for modeling systematically, which is the crustal scale, provides the overall architecture of the area. And it's a scale appropriate for computing the distribution of physical properties, like seismic velocity, density. So you transform this model to a density model if you have a gravity survey. Okay, this is the architecture, the basement. You have small scale, very, very small areas where they are dedicated to environmental studies. Detailed stratigraphy, facies, porosity distribution, generally used for transfer simulation. And you have some intermediate scale, like this one, which are here, which are used, for example, for seismic risk, alluvions, Triassic, Jurassic, Tertiary, and you must fill the model with seismic velocity properties to be able to simulate the seismic risk simulation, which could occur from the main fault of the rain graben, because it's a seismic area. So, but how do we go from this model to this model? How do we go to this model to this model? This model does not contain any information to go to this model. So actually the idea is to say, okay, the database shares all the scales, and depending on the scale, you extract the data to build this model, to build this model, or to build this model. But a model in itself doesn't contain its multi-scale aspect. Actually, this is only a concept for now. This is an idea, so this has to be implemented. But the way experimentally it works is this one. The database must contain information reliable on given scales. Okay, so the regional model of the Vosges is to illustrate here the Rhine-Graben. So we had to do it as well, and tertiary and the underlying geology. So with all the series of faults, when you switch off tertiary, when you switch off Mesozoic, you get all the basement rocks. You switch off the Permian, and so on, and so on. And the north area of Vosges, granodiorites, and to finally go to what was interesting, the granites, anatectic granites, which invades all this. So to take this into to model this, of course, this model takes into account cartographic data, but as well interpreted data for this party under, because no cartographic data for this. So this is an partially argued by mapping data, consistent with maps and consistent with what we could say geological interpretation. So the MGK granites and the diapiric zone, the diapiric extrusion of granulates. So the same. This model is consistent with foliations and outcrops, and with the hypothesis downwards. Sorry, foliation trajectories driven by foliations here from cartographic data, centered on the extrusion. So this model, so we wanted, so now that we have built a model, we want to test it against the gravity field. So Bouguer anomaly, where we switch off the effect of the MO because we model at 20 kilometers depth. So we have to remove the effect of the MO. And so on. Once the MO removed. So for inversion, in our case, we did hypotheses of 3 structural levels: infrastructure, gneissic dome, superstructure, and the zone of transition. Infrastructure is a dike here. Superstructure is anatectic granite, which invades everything. So in one first run, we did not distinguish different types of necks. And in the second run, we distinguished all types of necks. In this exercise, the geometry of units was fixed, assumed valid, and we wanted to test the distribution of, if density distribution could fit with the geometry. It means that the boundary of units are not modified during the inversion process. So only densities can be modified. Okay, densities, here are many formations, many granites and gneiss and so on, and schist. So you see not a lot of variations, so difficult to decipher between. Only the anatectic granite has a low density, which is a good idea. So the result of inversion for the first run, where we see that on the diapiric that something occurs here. but it cannot be really mise en évidence, highlighted if we don't distinguish Orléans unit. So this is a histogram a posteriori of densities within the granite. It means that and a priori and a posteriori. A posteriori is better than a priori, which is very rare in inversion. It means you gain some information. It means the density you give and the density you give, the density distribution is very narrow, more narrow than the one you gave. It means that it's not worth to try to change the geometry because you will not have more information. It means that with this geometry, it doesn't need to vary a lot the density to be honored. It doesn't mean that the geometry is correct. It means that we cannot get a better geometry. The same for gneiss granulitic. They get a better resolution after than the one we gave. The same for all types of gneiss. And you see that in the north, actually, there are two populations a posteriori. It means that we missed one type of gneiss in our model. But it was not the purpose, so problem. And then, so you can have all the granites has a strong contrast, and this model explains the gravity map. So, at least in southern parts. Here, it's more difficult. So, and here is, we switch off and we try to see, okay, the diperic structure, which occurs here. So, the diperic structure, with the densities that we know, all this model explains the gravity map. There is so the only thing we can say is that this model cannot be invalidated by the gravity. And so on, and the granite with the diperic densities. The density distribution doesn't disagree with the model. So, given the knowledge about densities, this is a problem because we have introduced knowledge about the density distribution, which was very mean, very rough. So the distribution obtained from inversion does not invalidate the proposed geometry for gneissic dome and granite. So this architecture is then a possible model until someone tells, no, it's wrong because. Indices aside, geometries have not been modified, but it was not useful because the allowed variations on densities are enough to explain the gravity field. Unless we know better constraints on densities, we cannot modify the geometry. So then if we want to go ahead on the geometry, thickness of granitic, roots of granite, depth of sedimentary units, it is necessary to progress on statistical knowledge of physical property. So the result is a geological model assorted with a distribution of density model. And we propose that this démarche, this approach, is systematically used in RGF projects. That means each project of RGF will have to build a regional scale model which is the basis for every model, where it will be assorted with relevant physical properties. We mean density, magnetism, seismic velocity, thermal, porosity, facies, etc. But at least density and seismic velocity are the most important. So this is a proposal. I don't know if it will be accepted. It is, for the moment, agreed, but we wait for the money to do it. And so this is the demonstration we try to make, that at least at a crystal scale, make a 3D model with physical properties. So there is necessity for acquisition surveys for these properties, of course. And of course, geological acquisition, traditional field, structural measurements, understanding the geology, the petrology, the geochemistry, isotopes, and all this. And of course, all this has to be integrated in database, modern database. So there is necessity to maintain, I would say, to increase the research effort on 3D modeling with all these problems that have been raised: uncertainty assessment, multi-scale modeling, big data set, geological complexity, interoperability between data, between models, common platform for data acquisitions, how do we deliver the model to society, and so on and so on. Thank you.